Hello, this video is on section 2.3, which is biconditionals and definitions. The learning target is to write biconditionals and to recognize good definitions. Now, a biconditional is a single true statement that combines a true conditional and its converse. Now, when you write this biconditional, you basically are taking your converse, which is flipping your original statement around and combining that with a statement that is if and only if. And I will use an abbreviation on this with the letters IFF, which stands for if and only if. So if you look at our conditional, and an example of this could be if the sum of measures of two angles is 180, then the two angles are supplementary. Its converse is taking your if-then statement and flipping it around, which is if the two angles are supplementary, then the sum of the measure of the two angles is 180. Okay, so this is our converse statement based on our conditional statement. Now the way we get our biconditional is to take out the if-thens, and in between our new hypothesis and conclusion, we plug in an if and only if. So a new biconditional based on our converse statement is the two angles are supplementary if and only if, which I'm using IFF, if and only if the sum is 180. So I've taken my converse, I've eliminated my if and then, and in between I have plugged in an if and only if statement. This right here is what determines the biconditional statement, flipping around the if-thens and including an if and only if statement. Now the symbols we will use in order to differentiate between some of the other conditionals and converses and contrapositives that we use is a P and a Q with an arrow pointing in each direction. And this tells us that the biconditional is P will happen if and only if that Q happens. So if we have a conditional statement, another example, where a ray is an angle bisector if and only if it divides an angle into two congruent angles. This is a biconditional statement since we have an if and only if statement already in there. Now our P of our biconditional is whatever is before the if and only if, which is a ray is an angle bisector. The Q is it divides an angle into two congruent angles, everything after the if and only if. Now I'm going to use this symbol as shorthand for an angle. And this is also the symbol that is short for congruent, to two congruent angles. Okay, so if we wrote an if P then Q conditional statement, it would be if a ray is an angle bisector, it divides an angle into two congruent angles. The conditional statement if P then Q, if a ray is an angle bisector, then it divides an angle into two congruent angles. Now the converse statement, which is if Q then P, is exactly what you see up here in the conditional, but you're flipping your if and thens. So if it divides an angle into two congruent angles, then it is a ray. Or then, not it is a ray, then a ray is an angle bisector. So I'm taking exactly what I see in my P then Q and just flipping it around to a converse if Q then P. If it divides an angle into two congruent angles, then a ray is an angle bisector. These are how you find the conditional and the converse statements. The last thing I want to go over is how to determine what a good definition of a term is. Now, a good definition is a statement that can help you identify or classify an object, especially in geometry when we're going through different shapes, points, lines, rays, segments, all those different terminologies. It's important for you to know what a good definition is. And these 3 tips help you determine what a good definition is. It uses clearly understood terms. You know all of the words inside the definition, and you don't have to redefine them over and over and over again. The definition is precise. It is exact. You don't use words such as large or big or similar. You are exact as possible and as precise as possible. A definition is also reversible, and a way you can reverse it is basically by taking your conditional and making a converse, taking an if P then Q and converting it into an if Q then P. That is the exact same thing as reversing the process. So if we take a quadrilateral definition, which is a polygon with 4 sides, the conditional statement of this definition is if a shape is a quadrilateral, and I'm going to say quad for short, then it is a polygon with 4 sides. So the conditional statement is if P then Q, which is if a shape is a quadrilateral, then it is a polygon with 4 sides. Its converse is basically what you see in a conditional, but flipping your if and then. So if it is a polygon with 4 sides, then it is a quadrilateral. Now, if the converse still holds true to our definition, then this means it is a good definition. If the converse is true, then we know that our original conditional statement, if a shape is a quadrilateral, then it is a polygon with 4 sides, then its truth value has held up. It is a good definition. So the biconditional statement is taking the converse, taking out our if and thens, and then plugging in an if and only if expression. So it is a polygon with 4 sides if and only if it is a quadrilateral. Okay, so this is how you find a biconditional statement based on the definition using the conditional statement and the converse. Once you've found that the conditional and converse both hold the truth value, then you can rewrite the definition into a biconditional statement. Okay, thank you.